Hello everyone, welcome to CH for us. Today we'll be solving few questions which have appeared in the NET examination.
In this question, organoborane is reacting with a compound containing halogen in the presence of palladium as catalyst and sodium hydroxide will give us a compound A. Now this compound will undergo hydrolysis to give us compound B. Now let us find what are A and B. So in this reaction, the iodine present in this compound will take the bond from carbon and will leave as I minus, and carbon here will get a positive charge. In this compound, carbon here will take the bond from boron and will get a negative charge on it, and this whole compound is eliminated with a positive charge on boron. Now, this negatively charged carbon will form a bond with a positively charged carbon, forming a new CC bond and will give us compound A. So this is the compound A obtained in this reaction. Now the reaction from here till the compound A is called Suzuki coupling reaction. So what is Suzuki coupling reaction? The reaction where organoborane reacts with a compound containing halogen in the presence of palladium as catalyst and sodium hydroxide, leading to a formation of new CC bond is called Suzuki coupling reaction. Now the compound A will undergo hydrolysis where ethoxide is eliminated along with H plus and the carbon here will get a positive charge. To this positively charged carbon, OH minus will attack, giving us this structure. In this structure, the bond between oxygen and hydrogen is shifted here, and the pi bond present between these two carbons is shifted to this carbon, where this carbon here will get a negative charge. Now the released H plus will attack the negatively charged carbon, giving us an aldehyde group at this position. Now here, oxygen, which is electronegative, will take the bond and will get a negative charge on it, and carbon here will get a positive charge. To this positively charged carbon, the lone pair of electrons present on nitrogen will form a bond, giving us a 5-membered heterocyclic ring, where nitrogen here is carrying a positive charge as it is forming 4 bonds. As nitrogen here is getting a positive charge, the bond between nitrogen and hydrogen is shifted to nitrogen, leaving hydrogen as H plus, and the released H plus will form a bond with the negatively charged oxygen, giving us an OH group. Now this OH is eliminated as OH minus, and this carbon here will get a positive charge. As it is having a positive charge, the bond present between this carbon and hydrogen is shifted here and H plus is eliminated, forming a double bond between these two carbons. And the obtained compound is product B. So in this reaction, we have obtained both compound A as well as compound B. Now let us see the next question. Here this reactant is having an alkene as well as an azide. This will undergo reaction in the presence of triphenyl phosphine, and benzyl oxycarbonyl chloride will give us product A. Now this product A will react with HgOAc taken twice, that is mercury 2 acetate and NaBH4 sodium borohydride to give us product B. Now let us find both A as well as B. So here in this reaction, nitrogen here is carrying a positive charge and this nitrogen is having a negative charge. So this positively charged nitrogen will take the bond from this nitrogen, and this nitrogen here will get a positive charge. Now this positively charged nitrogen will form a bond with the lone pair of electrons present on phosphorus in triphenyl phosphine and will give us a structure like this, where phosphorus here is carrying a positive charge and nitrogen here is carrying a negative charge. Now this negative charge is shifted here, forming a triple bond between these two nitrogens, and the bond present here is shifted with the nitrogen, leaving a negative charge on this nitrogen, and N2 is eliminated. Now the negative charge present on this nitrogen is shifted here, forming a double bond between nitrogen and phosphorus. Now this compound will undergo hydrolysis, where nitrogen here will take the pi bond from phosphorus, leaving phosphorus positively charged, and nitrogen here will get a negative charge. To this negatively charged nitrogen, H plus will form a bond and OH minus will attack the positively charged phosphorus, giving us this structure. Here, nitrogen will take the bond from phosphorus, leaving phosphorus positively charged, and nitrogen here will get a negative charge. As phosphorus is carrying a positive charge, bond between oxygen and hydrogen is shifted here, leaving phosphine oxide, and the released H plus will form a bond with the negatively charged nitrogen, giving us primary amine. Now here, protection of amine is taking place using CbZCl. So this is the structure of CbZCl. So this is the benzyl group and this is an oxygen. So benzyl oxy carbonyl chloride. So this is the name of CbZCl, that is benzyl oxy carbonyl chloride. Here chlorine will take the bond from carbon. Carbon here will get a positive charge, and nitrogen here will take the bond from hydrogen. Hydrogen will leave as H plus. So HCl is eliminated and the negatively charged nitrogen will form a bond with the positively charged carbonyl compound, forming a bond between nitrogen and carbon, and will give us product A. Now this product A is used in obtaining product B. So this is the product A. This product A will undergo oxymercuration in the presence of HgOAc taken twice, that is mercury to acetate. Here in product A, there is a double bond. This double bond is shifted onto this carbon, leaving this carbon positively charged. We know that tertiary carbocation is more stable than secondary carbocation, which is more stable than primary carbocation. As secondary carbocation is more stable than primary carbocation, double bond is shifted to this carbon and this carbon here will get a positive charge. In HgOAc taken twice, oxygen here will take the bond from mercury, leaving mercury positively charged, and oxygen here will get a negative charge. Now this acetate group will form a bond with a positively charged carbon, and this group where mercury is carrying a positive charge will form a bond with the negatively charged carbon, giving us this structure. Now this structure will undergo hydrolysis where acetate is eliminated along with H plus, leaving this carbon positively charged. To this positively charged carbon, OH minus is attached, giving us this structure. Now this structure will undergo demercuration in the presence of NaBH4, that is sodium borohydride, where oxygen here will take the bond from mercury and will leave as acetate. As this mercury is carrying a positive charge, hydride ion from NaBH4 will form a bond, giving us this structure. Here homolysis is taking place between this carbon and mercury, and then hydrogen and mercury, where Hg is eliminated and a bond is formed between this carbon and hydrogen, giving us this structure. Here OH minus is eliminated, leaving this carbon positively charged, and nitrogen will take the bond from hydrogen and will leave hydrogen as H plus. H plus and OH minus is eliminated in the form of water, and a bond is formed between the negatively charged nitrogen and positively charged carbon, forming a 5-member heterocyclic structure. So this is the product B. So in this question we have obtained both product A as well as product B. Now let us see the next question. Here this reactant is having an enol group which on reaction with trimethyl sulfonium iodide will give us a product A, which on reaction with trimethyl sulfoxonium iodide will give us a product B, and which on reaction with diiodomethane in the presence of zinc will give us product C. Now let us see what are A, B and C. So first let us find product A. Here in trimethyl sulfonium iodide, carbon which is present here will take the bond from hydrogen, leaving hydrogen as H plus. Hi is eliminated and will give us a structure where carbon is getting a negative charge. Now this compound will react with the reactant present over here, where oxygen, which is more electronegative, will take the bond and will get a negative charge on it, leaving this carbon positively charged. To this positively charged, the negatively charged CH2 will form a bond giving us this structure. Now in this structure, oxygen here is having a negative charge and sulfur is carrying a positive charge. We know that sulfur can form only, that is sulfur can exist only in +2, +4 and +6 oxidation states. As here sulfur is forming 3 bonds, it is having a plus charge on it. Now this positively charged sulfur will take the bond from this carbon and will leave as dimethyl sulfide, and this carbon here will get a positive charge. Now this negative charge present on this oxygen is shifted to the carbon, forming an epoxide ring, that is an oxidant or an epoxide is formed as a product A. Now let us find the mechanism involved in the production of product B. So first, in trimethyl sulfoxonium iodide, carbon here will take the bond from hydrogen, leaving hydrogen as H+, Hi is eliminated and carbon here will get a negative charge. Now this compound will react with the reactant present over here. Here the double bond which is present will shift to this carbon and a positive charge is obtained here. We know that tertiary carbocation is more stable than secondary carbocation. The double bond shifting is taking place over this carbon, leading to the formation of a negative charge on this carbon and a positive charge on this carbon. As this carbon is having a positive charge, negatively charged carbon will form a bond giving us this structure, where sulfur here is having a positive charge. As sulfur is forming only 5 bonds, it is getting a positive charge. Now this sulfur will take the electrons from CH2 and will leave as dimethyl sulfoxide, where CH2 here will get a positive charge. Now the negative charge is shifted over here, forming a cyclopropane ring. So this is the product B obtained in this reaction. Now let us find the mechanism involved in the production of product C. So first, diiodomethane will react with zinc metal, which gives a compound where zinc is present between iodine and CH2. Now iodine here will take the electrons from carbon and will leave as I-. Carbon here will get a positive charge. Now this compound will react with the reactant, where the double bond present here is shifted to this carbon, forming a negative charge on this carbon and a positive charge on this carbon. We know that tertiary carbocation is more stable than primary carbocation. That is the reason why double bond shifting is taking place towards this carbon. Now this carbon is getting a negative charge. Then the positively charged carbon will form a bond with the negatively charged carbon, giving us this structure. Here this carbon is having a positive charge. Now the carbon present over here will take the bond from zinc, eliminating Zni+, and will get a negative charge on it. Now this negative charge is shifted to the positively charged carbon, forming a cyclopropane ring. So in this reaction, we have discussed the mechanisms in the formation of product A, product B as well as product C.
For more such sessions, please do like, share and subscribe our channel. Thank you.